All right, so today we are looking at lesson 9.3 using reflections. We're again going to be looking at the marching band for this high school. The transformation is going to change our y coordinate from positive to negative on this transformation. So Maria, who is again at the x in our diagram down here, is going to move from the point 2, 4 to the point 2, negative 4. So in our transformation, she ends up here. This type of transformation is called a reflection. Reflections, you can call them a flip because the figure is flipped like a pancake, as the book says. But some of you may know it as a flip instead of a reflection. So mathematically, it's called a reflection. They give us a couple of the function examples for reflections. xy goes to negative xy is a reflection across the y-axis. On this one, your x value changed. Your x is your left to right values. If these values are changing, your figure is flipping across a vertical line, which is the y-axis if it's just changing the x values. Another example would be xy goes to x negative y. Since your y's are changing, that is changing in the vertical direction. And if you're flipping vertically, that is going across a horizontal line, which would be your x-axis. But you don't have to do just across the x or y-axis. You can reflect across a slanted line. This one in particular is where your x and y change positions, and that's whenever you reflect it across the slanted line y equals x. So they give us a table that they want us to complete for the two reflections. So the point 110, what changes here is the y. It changes to negative. So it would be 1, negative 10. For the point 6, 10, it changes to 6, negative 10. For the point 1, 2, it changes from 1, or it changes to 1, negative 2. And then the last point changes to 6, negative 2. The other image, they change the x value. So on this one, only the x value changes. So it's going from your pre-image to your image. Would be negative 1, 10, negative 6, 10. They give us the negative 1, 2, and then negative 6, 2. So I want to go over how we could do this using patty paper. So patty paper can sometimes help you with visualizing these changes. If you are at home and you don't have patty paper, you can use wax paper, parchment paper. They're basically the same thing, typically found in your kitchen. So let's look here. So this is what a piece of patty paper looks like. When you're using patty paper for these, you may feel like you don't need it. And if you don't need patty paper, that's fine. You do not have to use it. I just want to go over how you can use it so that in a minute it makes a little more sense with the next figure. So the first thing you're going to want to do is to trace your figure. And then you're going to want to trace your x and y axes because we are reflecting it across those two axes. So on the first one, that was a reflection across the x-axis. This is our x-axis here. And so when we go to reflect it, you can actually take your patty paper and fold it on that x-axis. And there is your reflection. So you can kind of see that it should be in the fourth quadrant, which is what they gave you over here. You can also take your patty paper and flip it over and then line up your x-axis if you want to see where it is. So that's another option there. And if you check, this top left point currently is at 110. When we make this figure flip over, it ends up at 1 - 10, which is exactly what we had in our chart, that it should be at 1 - 10. For this second figure that we were looking at, that would be going across the y-axis, which they weren't expecting us to graph, but if you were, you can fold it over, and there would be where it would line up. So the point that was at 110 ends up going to -110, which is what we had in our chart for that very first point. So that kind of shows you how you can use your patty paper. Now notice, every reflection is going to have a line of reflection here. And that is what is going to map your figure onto itself. If you took your pre-image and your image and you had them on one piece of paper and you folded them on the line of reflection, your figures would match up exactly. So that's always going to be how you can check to make sure that you've got your line of reflection in the right spot. So let's look at this next figure, dealing with an arrow. So they show you an arrow in this coordinate plane. The tip of the arrow is currently located at 410, which is right here. The arrow is currently pointing up. Notice that the graph is going by twos. 2, 4, 6, 8. It's not typically that way, but on this one it is. So they want you to predict the direction of the arrow after these reflections across the x-axis and the y-axis, and then to actually draw them and determine if your predictions were correct. So you can predict what you think will happen, and I'm going to show you using the patty paper how you can do these drawings. So you're going to take your patty paper and you are going to trace your arrow, just like we did our rectangle. And so if you take your pencil and you trace over it a few times, not hard, you're not trying to make an indentation, you're trying to put some lead on your patty paper. Like that. So you may be able to see there's some lead now. And then we are going to draw our X and Y axis. And you don't need to do that same idea with your X and Y axis. We're just wanting to make sure that our arrow has a good bit of lead on it. So we are flipping it or reflecting it across the X axis. So we're going to take this figure and we're going to flip it this way, turn our paper down. So you are going to take your patty paper and you're going to turn it like that. So I'm going to do it one more time. Since we're flipping it on the x-axis, we're going to take it this way, okay? And then you're going to line up your x-axis and your y-axis. And then you can take your pencil, or you can take your fingernail, or you can take like a penny or something that has kind of a edge, and you're going to just lightly go over your arrow. Or if you wanted to use your finger, I don't have much of a fingernail, but look, just do it like this. You could use a penny or a coin in the same way. And then when you move it, do you see how your arrow is on your figure? And depending on how hard you press down to transfer the lead, may mean that you have to go back over the figure, but it should give you at least a rough idea as to where your arrow needs to go. So when we flipped it across the x-axis, it is pointing down. So hopefully you had the right idea there. If you feel like it didn't transfer very well, then you may want to take your patty paper and go back over it again with some more lead. Some of you may have done this in like an art class or something, where you're transferring with chalk or charcoal or something like that. And this time we're going to reflect it across the y-axis. So it's going to go this direction. So we're going to take our patty paper and we're going to flip it over, kind of like you would a pancake. If you've never cooked pancakes, this weekend you need to ask your parents to let you help learn how to cook a pancake so you can practice flipping them over. And then you're going to again use something. You could use your finger like that. And there's my arrow. So those are your two reflections. So when it's across the y-axis, it's still pointing up. Then it asks for number 4. What reflection maps the arrow to a downward arrow that also has a tip at the point 410? So, downward arrow. If we flip it across the y-axis or a vertical line, it's still going to be pointing up like it is here. So we're not going to be flipping it across a vertical line. We are going to have to flip it across a horizontal line so that it's going to go to pointing down. So some of you may say, well, watch, flip it down and then translate it up. But what they are wanting you to try and find is a reflection that puts it here, and that's all you have to do. If you took your figure and you flipped it up, that would put it where it needs to go. So if I took it and I flipped it up here, that would put the arrow exactly where I want it to go. And so the line of reflection on this one, since the tip stayed in the same spot, this is going to be the line of reflection. And so that is a horizontal line. So that's a y equals. The slope is 0, so 0x. But that's just y equals. And then you got to look at your y-intercept, which is 10. So y equals 10 is the equation for that reflection. Then for number 5, it asks, could a reflection map the arrow so that it points to the left or to the right? So you might want to pause the video and think about that for a second. We were flipping it so that it was pointing down or up, but is there a way to make it point to the left or right with a reflection? You may say, well, if we turn it, but that's not a reflection, that's a rotation, which we'll look at later. So one way, yes, it can happen, and you're going to say no, some of you, is to do it at an angle. Do you see that arrow? It is pointing to the right. So I'm going to fold. That's one particular line right there, which that line has a slope of 1, so 1x. And then I don't know what that number is, maybe minus 6, but something along those lines, y equals negative x minus 6 would make it go to the right. So is there a way I could make it go to the right, to the left instead of the right? Yes, if you turned your paper the other direction. So if you had a negative slope. So that could be maybe y equals negative x, and that one actually went through the origin. So just turning it over there. But a slope of positive or negative 1 would make it parallel to the x-axis, but pointing to the left or right. So you don't have to have just horizontal and vertical reflection lines. So now let's look at the next page. We have Mr. Scott arranging the tuba players in an arrow formation as shown. Then the tuba players undergo a reflection that is described by this function. So without using patty paper, you can do this reflection. The easiest way to do this is going to be to pick some points on your arrow. So let's start with the point 4, 5. If you apply this function, 8 minus 4, 5, you end up with the point 4, 5, which means this point did not move at the tip. So let's pick another point, 2, 4. If we apply this function, we end up with the point 6, 4, which is there. So you may be like, what is happening to my arrow? So let's do some more. Looking at the point 2, 6. If you apply the function, you end up with the point 6, 6, which goes there. Another point that I could do, it's okay to have a fraction, 0, 4.5, 4.5. So 8 minus 0 gives 8 and 4.5. So we should draw that right here. And so hopefully you're kind of seeing what your arrow looks like. If not, pause the video and pick some other points and graph them. But here is your arrow. And so now if you want to check that that does match up, you could draw it on your patty paper and then flip it over and make sure that it looks right. Or they tell you, you could cut out a paper arrow and then make sure that it looks like it should. But a reflection should still look like it does, just turned, just look in a different direction. So now we want to identify the line of reflection. So since this red point, the tip stayed the same, we know that the reflection is going to be on that tip, and it's a vertical line of reflection, so the equation of it is x equals 4. Okay, so looking at number 7, which tuba players traveled the longest distance during the reflection? Well, the ones that went from here to here had to travel the longest distance. And so that distance is 8 units. The tuba player that did not move any is the one that is at the tip. So he's at 4, 5. So he didn't change positions. He just stood there. Then number 9 asks, explain why the reflection does not change the distance between any given tuba player and the point 4, 5. So what that's saying, the people over here, all of the marchers, the distance between them and this red point, 4, 5, why is it the same as their distance when they move over here compared to the point 4, 5? So a reflection preserves the size and shape of a figure. And that means that it preserves the distances between the points within the figure. Since the reflection maps 4, 5 onto itself, the reflection preserves the distance from each tuba player to the point 4, 5. In other words, a reflection is a rigid motion. So the pre-image and the image are the exact same shape and size. The points, the marchers keep the same spacing in between the points. Okay? So that is the easiest way that I know of to do this type of reflection, where when you look at it, you don't know what it looks like. Some of you may look at that and go, it looks like a translation, not a reflection. And the best way is to plug in points into that function and see what happens to them. So that's what I would recommend on that one. But that's not the only way that you can do it. You can do it other ways. Okay, so let's look now. On this page, we are skipping this entire page. We do not have the access for y'all to use the software in class. So we're going to be skipping this page. And now we're going to look at page 116, dealing with reflections off of the coordinate plane. So your reflection does not have to be only on the coordinate plane. Just like our translations that we looked at earlier this week, just like other transformations, your reflections can be off of the coordinate plane. So just like our translation, your transformation that's a reflection is going to map P, that's your pre-image point, to P prime, that is the image point. We are going to come back to these actually after we do number 13, because I want to have the figure to kind of explain those two. So this is the book's notation, R sub L. All it is saying is reflecting across line L. We're not going to use that too much in class specifically. It's not going to show up on your test, so don't worry too much about understanding that notation. I'll tell you what they mean while we're working through the book. So number 13 says that we are taking the pentagon and we are reflecting it. So yes, we could take the figure and we could just slide it over. But that is not what we are doing. We are not sliding it. That is one way to move the pentagon, but they want it to be reflected. And so we are reflecting it across a line that is somewhere in between the figures. Now, where should it go? It should go exactly halfway down the middle. This is where line L should go. The reason that it needs to go halfway down the middle, the distance here to the distance to this point, which is going to be B prime, should be the same. Same idea. This distance should be the same as this distance to A prime. And so that's what this first bullet point is saying. If a point is not on your line of reflection, then the line of reflection, we're going to come back to the perpendicular part, is the bisector of the point to its image point. So this line L cut this segment in half into those two congruent segments. And it's going to do that between every 2 points. When you reflect it, you're going to still be the same distance away from your line of reflection. Now, perpendicular bisector. These make right angles. So your line of reflection is actually going to be the perpendicular bisector. It's always going to be that way. So that's how it creates a perpendicular bisector. So then it wants us to label the rest of our points. So this is C prime, this is D prime, and this is E prime. Okay? That's all for 13. Now looking at this other bullet point, if P is on your line of reflection, then it's going to stay in the same spot. P and P prime are going to be the same thing. So if I look back, this person here was on the line of reflection, and that's why they did not move. So that point stayed as the 0.45. So now we're going to look here. Quadrilateral ABCD was constructed by drawing scalene triangle ABC. So we took this triangle here, and then we reflected it across the line BC. And they want us to prove that BC is perpendicular to AD. So when they say this, they're not meaning to do a two-column proof. They're basically just wanting you to explain completely how you know that they are perpendicular. So when we reflect point A prime ends up mapping to where D is. So the reflection maps A to point D. By the definition of a reflection, that means that AD, that line segment, is perpendicular to the line of reflection. That's part of the definition of a reflection. And so the line of reflection in this figure is BC. And so that's how we know that they are perpendicular. And that's all they were looking for on that one. For part B, how do we know that AB is equal to BD? So AB is this part here, and then BD is this part here. So the reason that we know that those are equal, D is again the image of A. It's where A prime should be. And reflection preserves distance. Reflection is a rigid motion. So AB, when it's reflected, its image is BD. And so that's how we know that they are equal. Okay, so now we're going to look at the next page. We're going to look at this second paragraph. It says, look back at that quadrilateral ABCD that we were just using. It was constructed by a reflection of that triangle ABC. That means that it has reflectional symmetry. Line BC is the line of symmetry for that figure. So what I want to very briefly go back over is something that you probably did in elementary school with scissors and paper. Did you ever take and draw a heart and cut it out? Did you ever fold a piece of paper and then cut out a heart? Maybe, maybe not. But a heart is an example of a figure that has a line of symmetry. Okay? Because when we fold it over, it should match up. So that is our line of symmetry there. Same way with that quadrilateral that we just had. So they gave us a couple of figures, and they want us to draw all the lines of symmetry. You can have just one line of symmetry, two, several, or you could have infinitely many lines of symmetry. So for this triangle, it only has one line of symmetry. And if you're looking at it going, I think it has more, I'm going to show you in just a moment with our patty paper how we can verify that it's only one. For the rectangle, it has a vertical line of symmetry and a horizontal line of symmetry. And again, some of you may be thinking it has other lines of symmetry, and I'm going to show you in just a minute how you can verify that. For the star, it has a vertical line of symmetry. And since we went tip to tip, we can do that at this angle and at this angle. We can also go horizontally from like the crease to the crease, and we can do that at those diagonals. So it actually has several lines of symmetry. It has 6 lines of symmetry. So we are going to look in our book at these figures. So you're going to take your patty paper and you are going to trace the triangle. So some of you may think that there are other lines of symmetry besides just the vertical one. So if I were to try and fold it somehow this way, do you see how they don't line up, those corners? No matter how I fold it, it's not going to line up. So this isosceles triangle only has that line of symmetry. For the rectangle, some of y'all are saying, no, it has a line of symmetry at the diagonal. So let's check and see. If I draw, it would look like that. Did that map it onto itself? No, it did not. So not a rectangle, unfortunately. And you can do the same idea with any figure. If you think it has a line of symmetry, then draw it and fold it on there and see if it works. Okay, so now let's look at the number 16. This triangle has 3 lines of symmetry, labeled L1, L2, and L3. What can we conclude about this triangle? Well, since we have this vertical line of symmetry, that means that this side, AB, must be equal to this side, AC. Because when we fold them on top of each other, they have to line up. Okay? So we know those 2 sides have to be equal. Looking at L2, if this is a line of symmetry, that means that AB has to be equal to BC. Which means if this side is congruent to that side and this side is congruent to that side, that this is actually an equilateral triangle. Since your reflections preserve distance, since your reflections are rigid motions, all of the sides are going to have to be the same length since they are images of each other. So that's what we know about that triangle. So now let's look at the next page. This is the check your understanding. So y'all pause the video and try 17, 18, and 19, and then I'll go over them. They want us to match the figures to their number of lines of symmetry. So below this, you can see that they have 1 line, 2 lines, 3, 4 lines, and infinitely many lines. So for an isosceles triangle, I'm going to start with that one. We know that it's only going to have 1 line of symmetry. So that's going to be what A is. For a square, it's similar to a rectangle in that it has a horizontal and a vertical line of symmetry, but it also has 2 other lines of symmetry. It can be reflected along its diagonal. And the reason that a square works and not the rectangle, this side and this side are congruent. They're the same length because that's part of the definition of a square. And on a rectangle, they're not the same length. And so that's part of why the square is going to have 4 lines of rectangle, 4 lines of symmetry. For a rhombus, it has 1 here and 1 here. And some of you may say, what about side to side? And so let's look at the rhombus. So you can always verify with your patty paper. And if you fold it this direction, it ends up not lining up. They go the wrong direction. So a rhombus only has 2 lines of reflection. A circle, though, will have infinitely many. You can do any number of them for the circle. Okay, so now let's look at this scalene triangle, ABCD, which means it has 3 unequal sides. Point D is on the line AC, and BD is perpendicular to AC. Why is BD not a line of symmetry for the triangle? Well, we know that AB and BC are not the same length. So when you reflect the figure across BD, they're not going to match up. And that's a good enough explanation there, if that's what you want to say. It's supposed to be a rigid motion, so the 2 sides should be the same. And if you look at it, the 2 sides are not. Does the triangle have any lines of symmetry? No. Since the triangle is scalene, none of the sides are going to be the same length. So when you're looking at the reflection, never are you going to have a side that matches up with another one because they're all different lengths. So it does not have any lines of symmetry. Okay, so now let's go to the last page dealing with the practice problems. They want us to draw the reflection of the arrow described by each of these functions. So easiest thing to do is to pick some points on your arrow. So I'm going to pick the point 0, 3. I'm going to pick the point 2, 2. I'm going to pick the point 2, 4. And I'm going to pick the point 4, 2.5. And so if you use part A to apply the function that they give you here, if you plug in 0, 3, you end up with the point 8, 3. If you plug in 2, 2, you end up with the point 6, 2. If you plug in 2, 4, you end up with the point 6, 4. And if you plug in the point 4, 2.5, you end up with the point 4, 2.5. So here is your arrow, which means the line of reflection is right here, which is the equation x equals 4. For part B, again, use those same points. If you plug in the point 0, 3, you end up with negative 2, 3. If you plug in the point 2, 2, you end up with the point negative 4, 2. If you plug in the point 2, 4, you end up with negative 4, 4. And if you plug in the point 4, 2.5, you end up with negative 6, 2.5. And so here is your arrow. And so the reflection line has to be halfway between these two. So it's going to be right there, which is going to be x equals negative 1, because that's halfway between your 2 arrows. For part C, we are going to be taking our points and plugging them into x negative y. So we're going to end up with 0, negative 3, 2, negative 2, 2, negative 4, and 4, negative 2.5. So your arrow should look something like that. And this time, your reflection line is this direction, and it's got to be halfway between. So it ends up being a horizontal line, which is y equals 0, which is on top of the x-axis. So then it asks, describe a reflection that would map the arrow onto itself. So on this one, you are looking for where is the arrow's line of reflection. Right here is where the arrow, if you flipped it on that green line, it would reflect onto itself. That is the symmetry, the line of symmetry, line of reflection for that arrow. And so that equation is y equals 3. Okay, so now let's look at this irregular pentagon. That means that the sides are not all the same length. A, B, C, D, E has exactly one line of symmetry as shown. What is the image of point C under the reflection across the line of symmetry? Basically, where does C get reflected to? It gets reflected to point D. This distance is the same as that distance. Does any point remain fixed under a reflection across the line of symmetry? Are there any points that are on the line of symmetry? Yes. Point A is on the line of symmetry. So point A is going to remain fixed. Since it is on the line of symmetry, that's the line of reflection, it is going to stay in the same spot. And then it says which sides of the pentagon must be congruent. So it's talking about of the 5 sides. There are 5 sides to a pentagon, and which of those are congruent? We know that this side and this side must be congruent. They must be equal. We also know that this side and this side are equal. They are congruent. And then those are the only sides that we know that are congruent. So hopefully that helped you with understanding how reflections work.